In chemistry and physics, we often encounter quantities like force, pressure, energy, and speed, but have you ever wondered how we measure them? These are not fundamental quantities like length or mass, but they can be derived from the basic ones. That's why we call them derived units. Derived units are formed by mathematically combining two or more fundamental units based on how the quantity is defined. For example, speed is distance divided by time, so its unit becomes meter per second. Many derived units have also been assigned special names to honor scientists, like Newton for force, Joule for energy, and Pascal for pressure. These units help us describe real world phenomena in a way that's universally understood, from the lab bench to a spacecraft. In this module, we'll explore some of the most important derived units you'll use across all branches of chemistry. Let's begin with some basic spatial properties: area, volume, and density. Area is calculated as length multiplied by breadth, giving us meter times meter or square meter, symbol m superscript 2. Volume takes it a step further, length into breadth into height, resulting in cubic meter, written as m superscript 3. These are vital when measuring gas volumes, lab vessels, or solid samples. Now consider density, its mass per unit volume. That's kilograms divided by cubic meters, giving us kilograms per meter cubed. This unit is fundamental in determining the concentration of solutions, purity of substances, or behavior of materials under pressure. For instance, water has a standard density of about 1000 kilograms per meter cubed. Whether you're dealing with gases, liquids, or solids, these spatial derived units are essential tools in your chemical calculations. Motion plays a crucial role in chemical systems, especially in kinetic theory and gas dynamics. Let's talk about speed first. It's defined as distance divided by time, which gives us the unit meter per second, abbreviated as m/s. Then comes acceleration, which is the rate of change of velocity with time. Its unit becomes meter per second squared, written as m/s squared. Both of these help describe how fast or how quickly a particle moves. Now take momentum, which is mass times velocity. When we multiply kilograms with meter per second, we get kilogram meter per second, a unit also known as Newton second. In chemistry, particularly when studying particle collisions and gas laws, these motion-related units provide deep insight into molecular behavior and energy transfer. Now let's move into the world of mechanical interactions, beginning with force. Force is the product of mass and acceleration. So its unit becomes kilogram times meter per second squared, and this is called a Newton. When this force causes displacement, we get work, and work done is force multiplied by displacement. The unit becomes Newton meter, which is named the joule. Similarly, moment of force, also called torque, is force times distance, and it too has the unit Newton meter. These quantities show up in thermochemistry, physical chemistry, and mechanical systems. For example, when an object is lifted or a piston compresses a gas, we calculate the work done using these derived units. The joule and Newton help us quantify energy flow and mechanical impact, concepts that lie at the heart of many chemical processes. What happens when we look at how fast work is done or how pressure acts on surfaces? These are described using three very important derived units: power, pressure, and frequency. Power is work divided by time, so the unit becomes joule per second, which is called a watt. This is how we measure energy consumption or transfer rate. Next is pressure, defined as force per unit area, that's Newton divided by square meter, and the unit is Pascal. We use pascals when measuring gas pressure in cylinders or vapor pressure in liquids. Finally, we have frequency, which is the number of cycles per unit time, or simply 1 divided by time period. Its unit is per second, which we call a hertz. From boiling point elevation to resonance in molecules, these units help us track how energy and force behave over time and space. Electricity is a core part of chemistry, especially in electrochemistry and redox reactions. To understand it quantitatively, we use several derived units. Electric charge is current multiplied by time, that's ampere times second, and it gives us the unit coulomb. Then we have electric potential, also called voltage, which is work done per unit charge. That gives us joule per coulomb, or simply volt. When voltage is divided by current, we get electrical resistance, which has the unit ohm and symbolized by the Greek letter omega. Finally, electrical power is voltage multiplied by current, and that's once again expressed as a watt. These electrical units are not just for circuits, they're critical in battery chemistry, electrolysis, conductivity measurements, and more. Understanding them helps you bridge the gap between electrons in motion and energy in action. So, why do we use derived units at all? Because they let us express complex physical and chemical relationships in simple, standardized terms. These units, whether it's Newton, Joule, Watt, or Pascal, are all built from the 7 fundamental SI units using logical combinations. And many of them are named in honor of pioneering scientists like Newton for force, Joule for energy, and Ohm for resistance. When you see an equation or a data sheet, these units tell you exactly what's being measured and how. They make formulas work, experiments consistent, and global communication in science possible. I hope this session helped you see that derived units are more than just expressions, they are the language of chemistry in motion. In the next topic, we'll explore how to represent and handle significant figures, errors, and scientific notation. Until then, stay precise, stay curious, and let every unit guide your scientific journey.